This is a Mod 410 Remote Digital Multiplexer, or RDM. It was part of the measuring and telemetry system of the Saturn instrument unit. I picked up this box about a year ago to use as like a really nice little simple self-contained project in case I got burnt out working on the big coupling data unit project. This isn't a strategy that I would recommend, generally speaking, because it has a very high likelihood of spiraling out of control and either becoming a much bigger project or just becoming yet another unfinished project for the project pile. In this case, it actually did work out for me, though. I did restore it. It does work. But the downside of working on this thing while burnt out is that I don't have a lot to show for it. I didn't record any footage, I took barely any pictures, I didn't write anything down, I didn't build harnesses. So this video is going to be an attempt to make up for that. I'm going to talk about what this is, why it exists. We're going to take it apart and look at each module individually, power it up piece by piece. I'll build some actual harnesses. And hopefully by the end, you'll have a much better understanding of this box and the telemetry system it was part of. Before we talk about what the Mod 410 is, or how it works, we first need to talk about why it exists. And to understand that, we need to look at the Saturn Pulse Code Modulation Digital Data Acquisition System, or PCM DDAS, which I'm just going to call the PCM system. The PCM is the central component of the Saturn telemetry system. It collects all of the digital and all of the analog measurements, packages them up into frames, and then serializes these frames out to the telemetry radios. It also acts as the master clock for the telemetry system. The Saturn PCM is able to accept 100 digital inputs and 6 analog inputs, which is actually shockingly few. Compare that to the command module PCM, which is able to handle 304 digital inputs and 365 analog inputs. The Saturn vehicle really doesn't have that many fewer measurements to telemeter, so why use a PCM system that's seemingly so much less capable? Well, there's 2 reasons. The first is actually weight. The Saturn stages are much larger than the command and service module. Imagine that you have 100 measurements that you want to telemeter, and all of these are being generated by something on the opposite side of the stage from the PCM. With the command module approach, you have to run 100 wires all the way across the stage between the measurement source and the PCM. What you can do instead, though, is remove the multiplexing circuitry from the PCM and put it in its own little box right next to the measurement source. This allows you to connect all of the 100 measurements to this remote multiplexer, and then only connect that multiplexer to the PCM through a much smaller number of serial wires. This approach can actually save you a huge amount of harnessing weight. The other major benefit, which is the second reason to do it this way, is configurability. There's actually a PCM on each of the 3 Saturn stages and in the instrument unit. And as you can maybe imagine, their needs are a little bit different. With this approach, you can select only the number and types of multiplexers that you need for your application, which saves both complexity and weight. The Mod 410 is one of those available multiplexer options. It multiplexes 100 digital inputs in groups of 10 onto 10 serial wires to the PCM. There's 2 Mod 410s in the Saturn, both of which are in the instrument unit, and it's one of those applications that is the reason why the Mod 410 captured my interest in the first place. This unit, known as RDMK, connects to the LVDA to route LVDC telemetry to the ground. Back when I was porting the LVDC and LVDA logic to an FPGA, I actually needed to write a simple Verilog model of the Mod 410 to test the telemetry circuitry. It's the only other piece of the instrument unit that I had to model in order to get my LVDC simulation running. So when a real one popped up on eBay, I was keen to get it and reverse engineer it and power it up and see how it worked. And on that note, let's talk about how it works. It's actually a reasonably simple box. It receives 2 clocks from the PCM, a 3.6 kHz sample rate sync and a 4 Hz frame sync, both of which are applied to 2 cards called timing logic 1 and 2. These cards generate all of the clocks and synchronization signals needed for the rest of the logic. They also produce the telemetry readout pulse, which is the synchronization signal sent to the LVDA to get it to emit its telemetry. The main clock generated by the timing logic cards is applied to 4 different counter cards, which divide their input clocks by 5, 6, 3, and 10 respectively. There's some nuance there with the divide by 3 and divide by 10 cards, but we'll talk about that later. Each one of these counters will generate n phases of its input frequency divided by n. So for example, the 5 counter, given a 3600 Hz input, will generate 5 phases of 720 Hz. All of the counter outputs, as well as a global read clock and a global write clock, are applied to a pair of cards known as patch B and patch C, which are how you program the Mod 410. These patches generate read and write pulses to 10 cards known as MCRs, or magnetic core registers, which I think are fascinating. They're exactly what they sound like. Each one of these 10 cards has 10 bits of magnetic core storage on it. When an MCR receives a write pulse from the patches, it will write the digital inputs that it's currently seeing into those magnetic cores. And then sometime later, when it receives a read pulse, it will replay back the digital inputs that it was seeing at write time. This replay data is latched into a card known as the PSR, or Parallel Storage Register, which briefly persists that information and buffers it out to the PCM, which is expecting it to appear from the PSR at a specific time. The patches can be configured to write into any number of MCRs at any time and read them back one by one in any order, again at any time, which makes the whole system very configurable. And that's more or less all there is to it. Something else that I should mention is that although the Saturn PCM and multiplexers were considered to be Saturn building blocks, they were used in other things too. As an example, this page shows all of the telemetry system components for the Apollo telescope mount, which flew on Skylab. And among those are 6 Mod 410 multiplexers. I bring this up because my Mod 410 has a date code of 1973, and I'm pretty sure it was not built for Saturn. It may have been built for Skylab, but I'm not sure about that because the part number doesn't match what was printed on that page. So this unit is actually a little bit of a mystery to me, but it's a Mod 410 nevertheless. It should be the same as all the others, minus the programming. The last thing that I want to talk about before we dig into the box is documentation. I had several references while working on this restoration, none of which gave me the full answer, but all of which were quite useful, and without which the restoration would have been much more difficult. So the first thing to talk about is the Astronautics System Handbook, which is an all-around great reference for just about everything in the instrument unit, and some Saturn things outside of it. It does have a paragraph on the Mod 410, which itself wasn't terrifically useful. But what it does have is the best block diagram of the Mod 410 that I've found in any document. This is remarkably useful. So I made great use of this. I'm sure that I'll be referring to it a lot throughout the video. The next set of documents are interesting. They have a little bit of a story behind them. So a couple of months after I got the Mod 410, an eBay seller started listing a whole bunch of lots of Charlie Bell's personal working papers. If you don't know, Charlie Bell was an engineer who worked at Kennedy Space Center, who throughout the years was kind of appalled at how much historical hardware and documentation was just being scrapped and thrown out. And so he made an effort to buy as much as he possibly could. And a lot of the spaceflight hardware and documentation that still exists today exists because of Charlie. A lot of the rote memory modules that I've dumped can be traced back directly to his collection. So anyways, before he worked at Kennedy, he actually worked at IBM on the instrument unit, on its telemetry systems, and their ground support equipment. And so I got a lot of those lots of documents, and in them there were some gems that ended up being extremely useful for the Mod 410. Nothing, again, that completely unraveled it, but some very, very, very useful things. And I'll be talking more about these sort of as they become relevant for this video. But these were another major resource. And then lastly, we have this document. This is a document that I did not use for the restoration. It is a really good example of me failing to do my research thoroughly. So it's a weird document. It has a terrible title, Design Data Stage Design. But what it is, what this volume specifically is about, is all of the telemetry systems in the S1C stage of the Saturn V. Now the S1C doesn't have a Mod 410, and so I did look through it back then, just to make sure, but unsurprisingly I didn't find anything about the Mod 410 in here, and so I set it aside. What I didn't appreciate back then is that the Mod 410 is more or less a copy-paste of the digital section of the PCM. And while there isn't a Mod 410 in the S1C, there are other multiplexers that talk to the PCM. And I guess as a result of that, it has a really detailed section on the PCM. And you know, in addition to just a lot of specs and everything, it has schematics of a bunch of modules from inside the PCM. And, of course, it has schematics of the digital modules in the PCM. And because the Mod 410 is a copy-paste, it uses the same circuit boards as the PCM. And so I had almost complete schematics of the modules for the Mod 410, including their pinouts and everything, just sitting in the other room while I did this restoration, and I didn't know it. And so I guess that's a lesson to research better. Anyways, those are the main references. If I put up schematics in this video, they'll be coming from this document. But that's it. Let's get into the box itself. All right, it's finally time. Let's get this thing cracked open. And for the big reveal, there we are. So it's kind of an interesting construction. I haven't seen this in other non-Saturn hardware, but this is pretty typical for what you would find in Saturn hardware. So lots of single cards that are kind of pressed in. They're held in very tightly. I'll show how that's done in just a second. So what are all of these cards? It's at this point that our first Charlie Bell document is going to come in handy. It is this black binder in which he stored excerpts of a whole bunch of different manuals that I guess he found useful. Now brace yourselves, because what I'm about to show you looks a lot better than it is. It is the Maintenance and Instruction Manual for the Remote Digital Multiplexer Assembly Model 410. This is the manual for the box. We did it. Unfortunately, Charlie has only given us 4 pages, including the cover page here. So we've got the cover, we've got the first page of the introduction, which has some nice information. we have a block diagram that is honestly not quite as good as the one in the Astronomic System Handbook. But then we have the names of all of the cards shown in their installation places. So this is unbelievably helpful. We know what all of the cards are, and therefore have a much better idea of both what they do and in what order we're going to need to power them on. So I'm going to get to pulling all of the cards out. It's quite tedious because they're held in there very tightly. And they only have these little loops to hold on to, and I don't have a proper card remover tool for these specific cards. So I'm going to get to that, and then I'll show you what the inside of this looks like without any cards installed. Alright, I got all the cards out, which was a struggle. But now we can take a look at what's actually inside the box itself. It has a printed circuit board with backplane connectors down here, and then it has something that I haven't seen in any other Apollo hardware, again, other than Saturn hardware, which is flex cables. Flex cables were very widely used in Saturn hardware, which is kind of fascinating for, mid-1960s. But there's flex cables between each of the connectors and the board on the bottom. And then holding the cards in place, if you can see them, there's these little sort of, there's these grooves that have little squiggly pieces of metal running down them. So these are very tightly compressing essentially the edges of the circuit boards to hold them extremely tightly in place so that they don't move essentially in the high vibration environment of launch. In addition to making the cards really annoying to get out, these haven't aged terribly well. You can see there's a broken one here. They kind of have a tendency to just sort of break off when cards go in and out. And so I don't like these at all. It's not a big deal that these have broken. The cards are going to stay in place just fine because I'm not going to be shaking this anytime soon, anywhere near as much as the Saturn V would have shaken it. So continuing to look around, these are the other four connectors with their flex cables running down. There's a little grounding lug there to attach chassis ground to one of the pins out here. Yeah, there's not a whole lot else to say about it. It is kind of unfortunate that the bottom of this box does have screws. I guess I'll show you. There are screws on this panel, and I can take them off, but then I can't get the lid out because that board is mounted to the lid and then the flex cables are connected to the board, and it would just be a big nightmare to disassemble this thing. So as much as I would like to get that board out, I don't know how to do it safely. So I'm going to leave it in there. Yeah, so that's the box. Let's get on to the cards. The first set of cards we're going to look at is the dummy cards, which kind of, as they sound, they don't do anything. There's no circuits on here at all. They're just blank boards with a connector. One of the sides is conformal coated for some reason. But there's not a lot to it. There's 3 of these. As far as I can tell, they were sort of placeholders. The backplane connectors that these plug into actually do have power and some signals routed to them. So I'm not sure if it was future-proofing kind of thing, or if there were other options that I don't know about of the Mod 410 that would actually do something with these slots. But in the Saturn variants, at least, there are 3 dummy cards. So let's get those into our into the box to start building this thing back up. Okay, we've got our 3 dummy cards back in, and now let's move on to a card that actually does something, the power supply. Alright, this is the power supply card. As you might expect, it's very dense. It's actually quite heavy. And it displays sort of an unfortunate theme that we're going to see throughout the rest of these cards, which is that it's almost entirely built out of these encapsulated little modules, which were sort of like the building blocks of a lot of the Saturn hardware, seemingly. They're not integrated circuits, they're just, little modules made out of discrete components that were then encapsulated. But most of the boards are built out of these. There's some things that escape it, like you have your test points up here, some transistors. These are potentiometers that allow you to trim the voltage of each of the 3 power rails that this thing puts out. This is the back of the board. It's all quite pretty, and it's all conformal coded, which makes it difficult to probe at things if you need to probe things. So on the subject of these encapsulated modules, it's time to look at another Charlie Bell document. This one, let me zoom out here. This one is labeled CIU schematics. The CIU was the computer interface unit, which was another box in the instrument unit. And it was made out of the same set of off-the-shelf, so to speak, modules, the little potted modules. And so this packet has schematics for a lot of them. Now the CIU and the Mod 410 didn't use the same set of these little modules, so this doesn't cover everything in the Mod 410, but it does cover some of it. And it's interesting. I didn't actually have to refer to these that much, but I will say that this page and the one before it have foreshadowing for something that we're going to talk about later in the video, and I'm curious if any of you are able to spot it. Anyways, let's get that power supply plugged in. Okay, we've got the power supply installed back in the box, and let's turn it on and make sure it works. Generally speaking, with restorations, it's always a good idea to power up the power supply in isolation if you can, just in case something has gone wrong. It might be putting out a lot more voltage than it should. You don't want to blow up all the rest of your cards. So if you can, you can't always, but if you can, isolate the power supply and turn it on first by itself, you should do so. The reason I'm doing it inside the box is because it makes the power connections much easier. I don't have to worry about all of the pins, I only have to worry about connecting to the power connector on the front. And so that raises the question of which one of these is the power connector. And to our rescue comes Charlie's black binder. The first document in this binder is the Saturn 1B instrumentation system's description. This seems like it would be an incredibly useful document. As with the Mod 410 manual, we don't have the whole thing, but it does have some great stuff. It has this block diagram of the instrumentation system that I showed earlier in the video, but also it has pinouts for the Model 410. So here we go. J1 is our sync inputs. J2 is our digital outputs. J3 is our power connector, 28 volts. J4 is the sync output that would go to the LVDA. And then J5, J6, J7, they didn't bother to give us the pinouts. And so, yeah, I have to beep that one out myself. But it's given us everything we need to put into the box as far as power and sync goes, which is super, super useful. So to that spec, I have built a power harness. So let me get that plugged in. So J3 is the top left one here, and we can just plug these into the power supply. I have the power supply set up for 28 volts, current limited to 150 milliamps, which is sufficient for this. You don't want to give it too much generally to begin with. It's better to have it current limit than to explode. But now we need to test its outputs. And fortunately for us, these test points up top are the ground and then the 3 voltage rails that this box puts out. And I love these test points. They're amazing. They are compatible with regular multimeter probes. You can just push it down in and it clicks and it's stuck there. So we can get our probes installed for the first rail, which is plus 12 volts. I'll go ahead and turn on the power supply. Okay, there we go. And 11.97 volts after 50 years. Not bad. I have not touched the potentiometers, by the way. This is just how well it's doing after being unpowered for so long. So moving on to the next test point, this is minus 6 volts, and it's even better, minus 6.00. Can't complain about that. And then our last test point is plus 6 volts, and it's reading 6.04. So all 3 power supplies are right on the money. No adjustment needed, no restoration needed. They are just working great. So that's a really good sign. It means we can power up all the rest of the cards without worrying about our power supply blowing them up. So I will get to that. Our next set of cards are the sort of control cards that take the synchronization inputs and generate all the clocks to the rest of the box. Actually, I'm gonna end it here. I ended up recording a lot more footage than I was expecting, and to keep this video from being an hour long, I'm gonna split it into a couple of parts. So thanks for watching, and we will continue our look at the Mod 410 next time.